Okay, so as promised, we'll talk about the vector space in which we are going to formulate quantum mechanics. But before doing that, let's review some of the basic ideas. Let's say we have an electron which is orbiting around a proton, and because electron because of its wave nature, the electron is going to go around this proton like a wave. Now you see, you have seen here, you see here that there is a problem, that if the electron does not complete its cycle, then its initial situation is going to be different than its final situation, and this sort of breaks the model in this case. So it is a very simplistic model, but the idea is simple. The idea is that n times lambda equals 2 pi r. If this condition is not satisfied, then the electron is not going to have this final situation as the initial situation. So this is required for the electron to keep going in this orbit, and this is because of the wave nature of the electron. And moreover, you see this n here. Now this n can be 1, 2, 3, and 4, anything, and we already have seen these are called quantum numbers. To contrast it with classical mechanics, we know that if instead of an electron, if we have, let's say, a baseball, now this baseball will also have a wavelength lambda, but it will be very small according to de Broglie's wavelength. If you use de Broglie's wavelength equation, lambda will be very small. So you see, n will tend to be a very large number for this particular case. So we put a small value of lambda here for a certain value of r, let's say an r of a hydrogen atom, n will actually tend to be a large number, and this is called the correspondence principle, which we already have discussed. So see that the quantization, the discreteness of system appears because of the wave nature. Moreover, this electron cannot be pinpointed that at which location does it exist. It's a wave, whether it exists here, here, or here. So there is also there's no precise way to tell that this is where the electron is located at certain point of time. So there's some uncertainty involved in the position of the electron. You can actually measure this this position, then you have to bombard it with a photon, and then you will get to know the position of the electron here. But in the process, what will happen that this electron will be knocked out, or will actually have a change in momenta because of this photon, and then the momenta will be unknown. So so overall the statement is that there is uncertainty involved in the system, and that gives rise to the probabilistic nature of the quantum system. And we will encounter both of these. So let's talk about this vector space. Now we see that n is a quantum number, and this quantum number is going to give different eigenstates, and which we actually also saw in the last lecture, that the Sturm-Liouville's theory gives us many eigenfunctions for different values of lambda, and these eigenfunctions can be also understood as different vectors, because eigenfunction belongs to eigenvalue, and they sort of encompass space. And so we are going to talk about vector space. Now the vector space in which we formulate our problems or solve our problems in quantum mechanics or formulate quantum mechanics is called Hilbert space. And Hilbert space has a property that, and you can denote it, let's say something like this, and it's actually complex inner is called a complex inner product space, and the important property of this Hilbert space is that on this space is something called dot product, which is defined. X and Y are vectors. Don't worry if you don't understand this. The idea is simple. This is the way we are writing the dot product. And one example of Hilbert space is the Euclidean space. We know that on Euclidean space, we know that A dot B, which is same as that, is AX BX plus AY BY plus AZ BZ. So a dot product is defined. Also, we understand how vectors are defined on Euclidean space. We write them as AX plus AXX plus AYY plus AZZ. We can also write them as column vector. So this is one example of Hilbert space. Now, you see, Hilbert space is not really a small space. Euclidean space is just an example of Hilbert space. The only important criteria is that this should be dot product defined. And we'll talk different properties of Hilbert space as we move forward. So, just to start with different definitions, let me remove this. Okay. So, first of all, if a vector psi belongs to some Hilbert space, and moreover there is another vector phi that also belongs to Hilbert space, then their sum psi plus phi will also belong to Hilbert space. Okay, now this is the way we are writing a vector here. This is a vector, and in Euclidean example, it can be understood like this. All the while, you can sort of find analogous definition in Euclidean space. So here, you can take an example of the row a column vector, some value AX, AY, AZ. So if you add this to BX, BY, BZ, and if this belongs to Hilbert space, this also belongs to Hilbert space, this whole thing will also belong to Hilbert space. Okay, and their scalar product, or the inner product, which we already have defined, is defined or written as like this, and this belongs to complex numbers. Now, for Euclidean case, we know that it's going to be just a number and not a complex number. But Hilbert space is bigger. Is actually Euclidean space is just a subset of Hilbert space. Then we also have complex variables that we can have vector space formed from complex variables that can act as Hilbert space. Moreover, as we know that it's almost unavoidable to not have complex vectors in solving problems in quantum mechanics, because we know that quantum mechanical problems will have wave nature embedded, and this needs to be taken care by having complex numbers, because we know that behavior of this sort, which we see in waves, always appear. So you see they are complex numbers. Anyway, so this and this phi actually can be understood as a row vector. Let's call this, I don't know, let's say bx, by, and bz. And if you look closely, then we know that is almost, for at least for Euclidean case, is sort of equivalent to this. Okay, so our column vector is like this, which defines this kind of vector, and just the when your angle part is like that, it is called is showed as a row vector. And actually Dirac is the Dirac who gave this kind of notation, and he called this ket and this as bra. So this is a bra, and this is a ket. Okay, so let's move forward with more properties of Euclidean space. Some of them I'm just writing them down. One of it can be something like this. You can open the bracket. Also, this is 0. This is not okay, and this is same as this, minus this equals 0. They are more like unity if it operates on psi equals psi. Also a b psi equals ab psi. Now this is something new which you have seen. What these AB are actually not the same AB. Actually, I should have written them differently. So I'll write them as A B psi equals AB psi. These are called operators, which do certain operations on psi. For example, simple example can be in Euclidean space. If you have a vector and you apply a rotation matrix to it, and you can rotate the vector like this. So this rotation matrix, which we know if you have this phi, is given as cos phi, sin phi, minus sin phi, cos phi, if I'm not making any error. Anyway, so this is sort of a vector, and you can apply it on a ket to get that. So, and as you can see, applying two and you can clearly see that you apply two rotation matrices on a vector AP, you sort of get this kind of, you can very easily verify this kind of relation. Okay, moreover, if your bra is same as ket, then this is always greater than 0. You know that the dot product of a vector with respect to itself is always greater than or equal to 0. Okay. This is an important property and should be understood properly. For example, phi psi is equal to psi phi star, which which actually means that if you have, now in this case you see there's a star appearing. If it's just Euclidean space, you know that AB is same as BA. But if it's not a Euclidean space but complex